Welcome back to the rest of chapter 8. In the previous part, you learned about the complete electron configuration, writing down the orbitals from 1s, putting the electrons in them, and now you learn how to write down the noble gas or core electron configuration, which is the shortened form of electron configuration. Now we are going to assign a noble gas to each electron configuration. Let's go back to the same examples we had in the previous video. For electron configuration of sodium, you had 1s2, 2s2, 2p6, and 3s1. Now I want you to look at your periodic table and tell me what is the previous noble gas to sodium in the previous period from sodium. Isn't it neon with 10 electrons, right? So if you write the electron configuration of neon, you will have 1s2, 2s2, and 2p6. So if you compare these two electron configurations with each other, you will realize that this part of electron configuration of sodium is similar to electron configuration of neon, but you have one extra electron in 3s in sodium. So how to write the electron configuration of sodium in the form of a noble gas, or we call it core notation or core configuration? Seems like electron configuration of sodium is similar to electron configuration of neon with 3s1 outside. Means that this noble gas, because noble gases are the most stable, have the most stable configurations. Why? Because in all of them, sublevel P is completely full. They all end up in having P6 in their electron configuration. So they have a special stability. So they act as a core for us. So you definitely need to put the symbol of this noble gas in the bracket, and whatever electrons and orbitals you have extra, you will put them after the noble gas symbol. The same for chlorine. Chlorine has this configuration, right? So you have, again, previous noble gas to chlorine is neon, right? So again, the electron configuration of chlorine is similar to neon. Which electrons extra? 3s2, 3p5. By the way, the number of electrons are left outside the noble gas show the group number. Sodium is in group 1, so you have 1 electron outside. Chlorine has 2 plus 5, 7 electrons, so it's in group 7 or 17. For iron, the same. This time argon is the previous noble gas, so the electron configuration will be argon with 18 electrons, right? So similar to this part, and then you have 4s2, 3d6. So these are called noble gas or core configuration for the elements. Try to learn it. After you learn how to write the complete electron configuration, always go back to the to the electron configuration of the previous noble gas, always previous noble gas. Write down the electron configuration, compare it with your element, put the part which is similar in a bracket and put the symbol of the noble gas, and whatever electrons you have outside, extra, you put it outside. The next thing, so far we just worked on the neutral atoms, right? What if we have an ion? What do we do with an ion? We worked on the electron configuration of sodium, right? Let's work on the electron configuration of sodium ion. Sodium ion has one less electron than sodium atom, right? Because sodium atom must lose an electron to form sodium ion. So if its electron configuration, let me change my color. It's 1s2, 2s2, 2p6 to have 10 electrons, right? Which other element has 10 electrons? Isn't it neon? So, electron configuration of sodium ion is the same as electron configuration of neon. Please pay attention. By writing this, it doesn't mean that sodium ion becomes neon. It just becomes as stable as neon, has the same electron configuration. So, we can talk about the general rule about metals. Sodium was a metal, right? It happens to all the metals. They lose electron, one or more electrons, to achieve electron configuration of their previous noble gas, just like for sodium. It lost one electron to achieve the electron configuration of its previous noble gas, which is neon. You can try it for any other metals. You work on magnesium, work on aluminum. For chlorine, chlorine is a nonmetal, right? Let's write its electron configuration of the chloride. Chlorine had how many electrons? 17. When it gains one electron, it has 18 electrons. So let's write its electron configuration. 1s2, 2s2, 2p6, 3s2, and 3p6, right? 2, 4, 10, 12, and 18 electrons. Which other element has 18 electrons? Isn't it argon? So again, chlorine gains an electron to become as stable as argon. So what is the general rule this time? Nonmetals like chlorine gain electron to achieve electron configuration of their following noble gas. So nonmetals gain electron, metals lose electron, metals go back to the electron configuration of their previous noble gas. Nonmetals gain electron to get the electron configuration of their next noble gas. So I want you to also know how to write the electron configuration of ions and their noble gas configuration. The next thing that you know after you write the electron configuration and maybe the noble gas configuration is how to draw the orbital diagram. In orbital diagram, we show orbitals with boxes or circles. In your book, you have the circles. I prefer to use boxes, either one. And you use electrons as arrows, pointing up or pointing down. So, going back to the same examples, we wrote the electron configuration. We learned how to write the core notation or noble gas configuration. Now, let's draw the orbital diagram for the electrons that are outside the bracket. How many electrons do you see in the s orbital and 3s orbital? Just one. And how many types of s orbitals did we say we have? Just one type of s orbital, right? So we need only one box for our s orbital. One orbital, one box. One box for every orbital. How many electrons do we have in here? One. By default, we show the electron. Oops. Sorry, I have some reflections of light here. I cannot see the board sometimes. Well, so the only electron in s orbital, when you have one electron, the preferred form, the default form is that you show it pointing up with an arrow pointing up. So s orbital with one box and the only electron with one arrow. Let's do it for chlorine. You have S, right? So it needs one box. How many electrons do you have in your S? 2. We are supposed to have 2 electrons with opposite spins. So one of them should point at top, one of them should point at bottom. to show the opposite spin. The side of the direction of arrows show the spin. They're assigned for spins. How many p orbitals we're supposed to have? Didn't we say 3? So we need 3 boxes. I put a rectangle and I divide it to 3 boxes. It's not a very perfect rectangle, but writing on this board is not very easy. All right. If you have P, D, or F orbitals, I mean more than one box, you need to, the rule is, to fill each box with 1 electron first. Then if you have more electrons, go back and fill them up. How many more electrons do you need out of 5? 2 more. So this is the orbital diagram for an S2 and P5. Ready to do it for S and D? Again, S, 1 box, 2 orbitals. You see, it doesn't matter what type of S orbital, I mean, where is the S orbital in the 3rd level or 4th level. S is always S, there is just 1 S orbital, so you show it with 1 box. How many d orbitals are we supposed to have? You remember, you memorized 5. So I need a bigger rectangle. 1, 2, 3, 4, and 5. How many electrons do I have? 6. So let me fill each orbital with 1 electron first. 3, 4, and 5. And the 6th one is going to be written like this. All right? So far you learned electron configuration, core notation or noble gas configuration, and then orbital diagram. The last thing at this part you need to know is magnetic properties. Some elements, when you hold magnet towards them, an external magnet like a magnet bar, when you hold the magnet, they are attracted or repelled from the magnet. But some of the other elements don't do anything. So let's find out what are they called and what is this attraction or repulsion or no reaction depend on. After you write the electron configuration and draw the orbital diagram for sodium, you ended up having 1 electron in 1 box, which represents 3s1. This electron spins, creates a magnetic field, and if I hold a magnet bar next to it, it's going to react. Why? Because this little tiny electron is going to create a magnetic field which reacts with the external magnetic field. If there is at least 1 unpaired electron in electron configuration of an element, such an element is called paramagnetic. Paramagnetic. I expect you to know the names. So a paramagnetic element is an element which has unpaired electrons in its electron configuration, and it will react towards magnetic field. For magnesium, all the electrons are completely paired, so there would be no reaction towards magnetic field because there is no internal magnetic field to react with external magnetic field. If all the electrons in the electron configuration of an element are completely paired, such an element is called diamagnetic. Diamagnetic. There would be no reaction with an external magnetic field. And we all know that iron is attracted to a magnet. Now you see why. Because the electron configuration was 4s2, 3d6, you drew the orbital diagram, and you see that not only 1 but 4 unpaired electrons create a very strong magnetic field, and you will have a strong reaction with an external magnetic field, which makes it a strong paramagnetic element. Right? You can practice it on different elements. The last thing in this part is isoelectronic atoms or ions. Isoelectronic means same electrons. same number of electrons. Which means same electron configuration, right? So in order to find isoelectronic atoms or ions, simply just count the number of electrons in each. Sodium atom has 11 electrons, right? It loses 1 electron to change to sodium ion. So how many electrons will it have? Sodium ion, 10. Neon has how many electrons? 10 electrons, right? Because it's element number 10. And fluorine. Fluorine, the neutral fluorine has 9 electrons. It gains 1 electron to change to fluoride, so it has 10 electrons. So you see sodium ion, neon, and fluoride, so far they all have 10 electrons. Last one is oxygen. Oxygen, neutral oxygen has 8 electrons. It gains 2 electrons to become oxide, so again 10 electrons. You see sodium ion, neon, fluoride, and oxide, they're all called isoelectronic to each other because they all have the same electrons. So isoelectronic atoms or ions are those who have the same number of electrons. We are done with electron configuration. In next video, I will talk about periodicity or some trends that repeat in the periodic table.